invite you all to this special session, Narlikar session, as a part of the conference on Rethinking Cosmology. I think it's a great occasion to, kind of sort of remember Jayant Narlikar, who was a doyen of Indian science, who passed away May 20th this year. He is, of course, a globally renowned Indian cosmologist, a distinguished science statesman, community builder, communicator, and perhaps most importantly, a phenomenally gifted institution builder. So Professor Narlikar was deeply committed to creating and sustaining scientific excellence throughout the nation. He established a vibrant group at Tata Institute for Fundamental Research when he returned to India in the 70s that focused on gravitation and cosmology. And over nearly two decades there, he mentored a number of excellent scientists, many of whom set off to lead new directions in frontier research, in cosmology and gravitational waves. And I think in my, reading, a couple of points that make him really stand apart, even amongst the Indian greats, are his fine sense of fairness, equality, and his unwavering commitment to every cause that he believed in. Popularizing science, empowering the university sector in India, and openly confronting pseudo-science-based superstitions and astrology in India. I think there are very few scientists who, stay steadfast against whatever comes from the, opposition. So this session in the conference was envisioned as an opportunity to present perspectives on Jayant Narlikar as a cosmologist and his role in establishing a vibrant Indian presence in cosmology and gravitation. And of course, speakers would have their own interpretation and this thing. I should really acknowledge that the suggestion for holding this session was made to me by Professor Dick Bond, Dick here. And I'm really glad that Dick is here. He's, of course, an eminent cosmologist. But very importantly, he has had a very long connection to the Indian cosmology community growth in the post-1980s. Okay, so he was, of course, the director of Canadian Institute for Theoretical Astrophysics, where a number of us were postdocs and have had the opportunity to, get exposed to some frontier research. He has, as I said, can rightfully take pride in having trained Indian researchers at CETA, who have in turn gone on to, contributing to what you see as the cosmology and gravitation community in India, which is fairly, burgeoning and rich. Just a few words of introduction. Of course, he is very, very well known with many accolades and recognition, most recently the Shaw Prize in 2025, Legacy Fellow of the American Astronomical Society, and the Gruber Prize in 2008. And I don't want to really go back. He is, of course, Canada's Order of the British, whatever. So on all kinds of things. So, but more importantly, he is like a big figure in cosmology, and he has had the also the chance to overlap with the community with which Jayant scientifically and cosmologically, sort of worked with, and that's a nice perspective to have. So with that, let me invite Dick to say pay his tribute to Professor Narlikar.
Where did it go? Oh, there it is. Think of me now as Varun, because Varun was supposed to be here doing this, and unfortunately sickness happened, and so I'm doing an extended session, aren't you pleased? But in some respects, I may be one of the best people to do this because you'll see that my roots and Jayant's roots are kind of closely aligned, and it comes out of nuclear astrophysics, which gave birth to particle astrophysics, of course. But basically, it was the thing that started the whole ball rolling. And you heard me say a few words about this in my lecture on Monday. This will only have one of those kinds of slides. But there will be a lot of personal reminiscences of various people, because the story of Jayant is a story of the fantastic people that were precursors of this group. And I asked Varun to send me a picture of a tree. And in December 1992, there was a dedication ceremony at IUCA, and I was on the second grouping of people that were advising Jayant on how things should go. And so it was planted, whatever that Latin means. And so I did have a picture from 2001. The tree was flourishing, and this is the tree now. And so that will be my theme, and the theme that I will end on, which is Jayant having himself planted the trees, namely what all you have become, and you're all bearing fruit. And so that's what I'm going to end on, but that's what I'm beginning on, which is his tree motif, which he used extensively, by the way. So just for fun, I went through a series of the listings. They did an annual report every year, I'm sure they still do. And so this shows how things began. And you will see that what he did is that he drew for his roots everybody that he was connected to in England and in the US, Caltech, etc. And so this was the first annual report, and this was the Scientific Advisory Committee. I became a member of that committee in the second tranche. Has the greats, right? But you will see that a lot are nuclear astrophysics, and those with Indian names here you'll recognize were the major figures in India at the time, and that continues to have been his modus operandi. He brought the very best people to give him advice, and they were all connected in a network that was one of the reasons that they could rise so quickly. So Aduz, good friend; Jeff Burbidge, good friend; Radhakrishnan, you know all about him. Where was he? Raman. Martin Rees, not too shabby. Sarma, Raman, and Wampler. And they had made honorary fellows, and they're all the usual people that you might expect. The only issue with that is when the people died, they go off the list of honorary, and it was kind of poignant to see who left the ranks of the honorary fellows of IUCA. Chandrasekhar, numero uno, not so bad. Fowler, here, my thesis advisor, but deeply connected to Jayant Narlikar. Hewish, got some kind of prize. Sir Fred Hoyle, who was it is labeled as the guru of Jayant. Actually, Jayant, I think, was the deep calculator. And Hoyle, as Fowler told me, he would have a new idea every breakfast. And most of them were good. He was an amazing being and has historically not perhaps been as appreciated as should be. And I'm going to try and convince you that he is at the heart. On the other hand, what happened, anyway, we'll get into this. Salam, obvious. Just a few of the events. visit of Professor Chandrasekhar while the meeting of the Scientific Advisory come on. And I couldn't resist this because this was next on the agenda. There was a battle of cricket between Iuka and Tiffer. And, you know, that's as Indian as you can get. Well, you might say it's as British as you can get. And sometimes even Canadian as you can get. And so there were some colloquia, and I only chose these colloquia. It was just an ordered list. Nityananda, extremely well known. I actually don't know Gadgil. Chandra. Schutz, gravity waves, still doing it. Herman Bondi. Gold and Hoyle, that was the original steady state. And there's Fowler, happy to say, talking about the early universe. His early universe is not my early universe. We're so much earlier because they were nuclear astrophysics. That was the ultra early then. And the other thing here, apart from our good friend Jayant with Chandra, we have the two Burbages. Burbage, Fowler, and Hoyle. They'll return once again. And then what I was delighted to see in 89-90 was the commitment of Indians that had really powerful positions in the United States, Canada, and elsewhere in Europe. And they all were drawn together here by Jayant Narlikar. And so here's Sri Kulkarni. And then I noticed in one of them, just even a few years later, he gave, I don't know, 5, 6 lectures. So he was committed, and they were all committed. And the people who didn't have Indian origin were all committed. And so that's what actually made it happen at the speed that it happened. There was a huge community of what you might call superstars that came in order to lend their support to the vision that Jayant was trying to create with the Iuka concept, which is one of the great concepts, and India should be incredibly proud of it. So now I'm going to shift. Don't worry, this is not about me, although I did talk a lot about Gamow, because Gamow was one of the greats. And then the way science is portrayed is people love adversarials. So then it was Hoyle against Gamow, a Big Bang steady state. He never used Big Bang. And Hoyle, I will have a little anecdote, so I won't go too much into it. And there's Jayant, and I gave them all a gold star. But what I want to try and get across, because I knew a large fraction of these people, but it was before my scientific time. This is the Institute of Theoretical Astrophysics in 1967 in Cambridge. It began 1 year earlier. That was Hoyle's vision, and he brought all sorts of people together. In particular, when they started it, tell me if that's not Narlikar. Of course it is. Who else could it be? I hope. Because he looks a little bit different than the later things. But in any case, he did his PhD in Cambridge. He went off to another British university, but then became a founding member of this IOTA. And it was a remarkable thing, and I know about it firsthand because I was a graduate student at Caltech, as I said, before my time. But what would happen is every summer, there would be an army of Americans who were connected to Fowler and the Burbages because they were San Diego, and they would all descend upon Cambridge. Now that's been ongoing for all of these years and decades, but this was the beginning of that, and it was an amazing centerpiece for what happened and why Cambridge became such a center. It already was, Eddington and all of that, right? But this was really fundamental. So I have 3 rings for various reasons around Fowler. That's Hoyle. These are the 2 Burbages. And there are other people who are heavily involved in the nuclear astrophysics of the day, but it was Hoyle in the 40s who had the idea that there would be an iron peak that could be understood, the origin of the elements. And he played that game, got Fowler engaged, and they wrote the Bible. It was called B squared FH in 57. Again, before Jayant got into the game, but extremely famous and one of the remarkable developments in all of science, not just astronomy or nuclear science. But when the microwave background got discovered, they went into what Willie would have then called the early universe. And so that was Wagner, Fowler, and Hoyle. And so they nailed that problem. Peebles is no slouch. He did a big piece of work on this. But this was the definitive work on the Big Bang nucleosynthesis. And that, again, was before Jayant's time. But they already had the concept of the steady state universe. And we will see that the steady state universe is essentially the standard model of cosmology. That's going to startle you. I will explain it. And I have a little anecdote about that, which I'll say a little bit later. So I could wax eloquent on everybody here because, as I said, I knew them. And it was a remarkable group of people that made the scaffolding upon which everything that you do was based. So Jayant got in the game with, clearly he was recognized as being very, very clever. And as you know, he had a remarkable family in India, very, very distinguished. It was one of the reasons he could pull off an IUCA, because he was connected. And that connection meant that the government was willing to listen to an outrageous idea, which was the IUCA concept within the Indian context. So Narlikar, PhD, 63 in Cambridge, 66 to 72, a founding member of this fantastic group of people that used to come every summer, but of course it would continue through the winter. Then one of the most ridiculous things happened in the history of astronomy. There was a polarization rift. And it was not Hoyle's fault, it was Ryle's fault. He was a snobby kind of guy. Those who are radio astronomers, close your ears. And so they tried to do a revolution when Hoyle was out of the country to make an appointment, and he was mad, came back, resigned almost immediately, 72, and that's when, maybe it was all ordained, that's when Jayant returned to India and took over the group in TIFR, or however you say it. TIFR is what I say, but probably that's completely wrong. Anyway, Tata. And he drew a group around him there, and they were fantastic. But what he never did, because as we'll see, but I will try and convince you otherwise, his research, because it had the Hoyle association, was considered to be outrageous by the powers that be, and the powers that be were, in my view, pretty stupid egos. And I'll get into that a little bit later. But that caused the rift, but that is why the Jayant returned to India to do the heavy lifting that he did. And now I'm going to go back to the development of the times when I was explicitly involved in the vision that he presented to help him make the cause. And there I am. You know I look exactly the same, right? They all look distinguished, and the centerpiece here doesn't look very distinguished. But here is an extended group of the honorary fellows, and there are a couple of names that I want to emphasize, and it's not the Brits or the Americans. It is some of the people that I actually met there, but I don't think I ever met, I probably did actually, Ray Shaduri. You all know the name, right? So there were these fantastic people, but they were all spread out in India, and he helped to draw them together under the guise of honorary fellows. I guess they knew each other very well. Vaidya, another remarkable person who did fundamental things in the theory of relativity. It was involving a metric associated with radiation. But Ray Shaduri, in my talk on Monday, I'm sure it passed you by very quickly, but Ray Shaduri was one of the important names in how we actually do the calculations in general relativity, including the full development of the cosmic web. And so that's a name. And then there was another guy who I don't know, and I don't exactly know what he did. What I know is that they were saying, oh, Powell is here. He's fantastic. He's amazing. And I think it was partly because of his spirit. This is the guy here, and I can't resist showing it because isn't that an interesting picture of a being? But you will know better than me who exactly was. This is the Foundation Day lecture was given by Ray Shaduri, distinguished character, clearly. Okay, so now to the next one. Unfortunately, the one where I actually did the planting, well, I don't know anyway. Here's Hoyle giving a talk called An Unusual Adventure. What are you pointing to? And so what? What? No. Well, were you even born? Is this virtual? No, seriously? Where? Oh, here. Far out. I wish I had known that. You would have gotten a gold star beside you. So Hewish doing a tree. This was, I guess, the year before our trees, although it seemed like it was the same one. Burbage doing the tree. I don't know what their trees are like. Our trees are good. They've really grown nicely. And then he decided to have a road naming ceremony. So, you know, this guy has got the whole game being a director, right? So he does the trees, and then he does the road naming to get all of these luminaries to name the roads because he's bringing them together in order to try and further his cause. Absolutely amazing. And then the other thing that I grabbed from this little bit is the dots of what they were up to in the non-trivial, pardon the expression, country of India to try and actually bring it all together in a common cause vision that would take the extremes and bring them in, and there would be a network connection to IUCA that was going to help to raise all of the universities. Because historically, India seems to have been dominated by the institutes, including the Raman Institute. Fine, but they needed to make the connection to the universities, you know this very well, to get the people who were there teaching day to day, but they weren't getting lifted up in the whole vision of research. And IUCA drew them in, and for some period they would have some kind of fellowship with IUCA. They would be able to come and stay there, and most importantly, they would interact with themselves and everybody else. And it was really a fantastic vision, and it was driven by Jayant without a doubt. I'm still here, looking older. No, I'm joking. Okay, that's 93, 94. Okay, this is missed a year there, 95, 96. I put that up there because I've dropped off the center of the universe, which was in IUCA. And Richard Ellis came on, Friedman came on, and so Kei Sato came on. And you can see that he was still choosing the people that could make a difference in their connections to the external world. Honorary fellows, much the same names. And, oh yeah, I guess we went off in December of '94. Lyndon Bell was with me, and I must say Lyndon Bell adored being in India and being associated with this. And it's, I hate to say it, it's because he may have had fond memories for the Raj. But anyway, he loved it and loved the possibility of going to Ladakh to do hiking, etc. Anyway, so this was the group at that time. That was the end of my formal relationship as a member of the committee. But that didn't mean it was my last time there. And I'm going to show this just to show that wildness did happen. This was a meeting that we had. There's Varun Sunny. That's Sergei Shendarin, whose name was invoked today. He was clearly thinking about catastrophes. This was something which, fortunately, I didn't partake of, which is Indian vodka. I do not recommend anybody having India vodka. But what I want to get across here, and it was, I thought I would find a gentler picture, but this is the one that came up and it said, you've got to show this, because it shows you what it is that makes a scientific community really fly, which is the personal connections, that the spirits are up, and then under those guises you can think and talk the greatest ideas. And I will not say that the ideas that we were talking about that night were brilliant. I don't know if you can see, anybody who's in Europe, they might recognize this guy, really young, but I'm not going to go into that. Anyway, Sergei deserves to be in this picture because he had a long association, not on the committee, but with IUCA, just like Starobinsky did, so there was a big Russian connection. Okay, and I'm going to go back. Why am I going back to this? I already showed you everything about this. Good. What I am going to show you is this was the last picture of the group that were coming to IOTA in this summer. And curiously, oh no, see, I've hidden them. Terrible. Coincidentally, Roger Blandford sent me this picture because he thought I might be this person here. And I disabused him of that because I wasn't really scientifically, well, I was at the University of Toronto, scientifically born. But there are so many people here, fantastic beings. Obviously the Fowler-Hoyle combo, which was one of the great combos in all of astronomical history. Wal Sargent, Dave Schramm, fantastic character. At Clement wrote the book of Willie's lectures. Steigman, it'll come to me, don't worry, but it doesn't matter if it does or not because this is the most important being. I'm just trying to give an indication, though, of what the group was like that would come, and this was bigger than usual. There's Martin Rees. That is Jim Gunn. And I think, because somebody invoked this here, I think that's Grishuk. Do you know? What? Yeah. Yeah. This is Yahil, I think. I'm trying to figure out if that's Arnett. But in any case, oh, there's Woosley. I mean, these are the giants of the whole nuclear astrophysics. It all happened in that transport from Caltech back and forth, drawing the people in. And that's probably enough of that story here. And we'll go on to the next one. But I will end, one of the things I'll almost end on. So obviously I'm making use of the name giant in a stupid little way, but it's true, a giant in India. Tata, the period. And then, you know, as my collaborators know, it's very difficult for me to get anything out the door. This guy wrote 49 books in all of the languages, you know, many English, of course, but also in every language, as far as I know, in India. And that had an impact which was outsized, because it was an ability to draw in the entire nation into the story of cosmology. And if you think about it, Hinduism is also a story of cosmology. And so he was remarkable. 49 books, I think 3 or 4 were science fiction novels trying to mimic Fred Hoyle, who was a really great popular writer as well. But actually Jayant even more so here in terms of his impact in India. He wrote popular articles galore. He would put them out all of the time, and it was all directed in order to raise everybody up in the general Indian scene in order to make things happen at a higher and higher intellectual level. He created something, it was called Sci-Pop. Good name, huh? An initiative that it happened a little bit after I was on his board, but it was an outreach thing. But he was always doing outreach, but this was formalizing outreach and making all of the institutes in India get on board for the outreach. And the outreach here, I think, is as important as it is anywhere. And I think that it's played a big role. And even I got into the outreach game because I wanted to go someplace after one of the meetings. It ended up to be Darjeeling and Sikkim. So he set me up with giving a talk in Siliguri. And Siliguri is in West Bengal, and I'm sure many of you know of it. But it was an example of the connection to a university that would essentially not have had any interactions with the highest level of science except through the existence of IUCAA. And I was delighted to see that it is ongoing, that interaction with Siliguri. But it's, you know, that's just one of the many examples. It would be good perhaps to find the current version of how that outreach is all occurring in terms of populating. Anyway, it was just fortuitous that Roger sent me this, and not fortuitous that I blocked out Jayant. Okay, now I'm going to spend a little bit of time, sorry about this, telling you about his science, because this is going to be my fundamental statement here, because they did brilliant work, but there are big egos in science. Does that come as a surprise to you? And what that means is their minds are actually locked. They are not flowing freely. And so when something is happening that is not in their specific doctrine, then they'll pillory it. And that is ridiculous, because the only way that we can progress is by trying many things. And so I'll have a comment about that later. And what Jayant did, here he got the second highest honor in all of India. I don't know that much about it, but I thought I'd put a medal up there. But what they pushed was conformalism. And that's not conformity. It is one of the more exciting things that ever happened in general relativity, the recognition that the conformal factor, which multiplies g mu nu, omega squared, could in fact be dynamical. It's come to be called the dilaton. And they weren't the first ones to say, let's go for it. It was Jordan. But that was around 1950. And then Lyman, the great Dickey, came along and kind of clarified it and did fantastic work, and it's called the JBD theory. And I worked on it myself quite a bit, and it's beautiful, really beautiful. But Hoyle and Narlikar also came up with a conformal theory. It's now called HN theory, so it's great that it's transcended and has a name equivalent to the JBD, and it's really innovative. And then that whole concept transcended into what were called scalar tensor theories that were much investigated. For example, Bob Wagner of the nucleosynthesis calculations spent, a considerable fraction of the 70s working on scalar tensor theories as a general thing, where the tensor is obviously the metric tensor of general relativity, and the scalar, in this case, is usually the dilettante, doesn't have to be. There was a lot of fun at that time at Caltech with this idea, and I'm just going to give you an example of how outrageous everybody was back then. Because you see what it did, what they were doing, is that their idea was that they would have this conformal factor that would be like a scalar field, but it would be like a scalar field with waves. And so there would be a plus and a minus and a plus and a minus. And where the zeros of the scalar field were, you could interpret as a Big Bang. And that was a really exciting concept because that meant there was a before the Big Bang. And of course, a lot of people have said, what is before the Big Bang? That's a game that's been played by many, many people. But they were really, in my view, the first people to be so outrageous to make such a statement. And then the idea was that you have these plus minuses, and then essentially what you're doing is you're taking the a squared of t, if you like, and you are making it go through 0, but that's just the node. And so you have something that happened before. Then the issue is what happens when you pass through that 0, and that's, I think, where they may not have gotten the whole story, and I'm going to get into that in the end. But here was one of the ideas at Caltech. I know we were taking it very, well, I wasn't taking it, but Stan Woosley, they were looking for it, which was that you might have had a prior generation of stars. The generation of stars may have made iron cores. Those iron cores would pass through time 0. Then they would accrete more things, and the center of the sun would have an iron core. And we'd better look for it because that will solve the solar neutrino problem. Think of that. Isn't that fun? Doesn't work. And we learned that the solar neutrino problem was associated with the oscillation of neutrinos and flavors that, not flavors, but the mass. There's an oscillation of flavors and mass. Okay, but anyway, that was really fun. And then the issue was, oh yes, but don't the stars expand and they become fuzzy before they pass through? What implications? It was really an amusing set of thoughts. And at least it's deep as many of the thoughts that we all have now. So I like the ideas, but I always did, of this dynamical dilettante as a graduate student. And so I always played with it. And then we developed with Salopek something we called the variable Planck mass model, which just is much the same idea as Hoyle-Narlikar, which is that you've got the Planck mass, which is a function of some field. And there are two fields that are considered. One is the scalar curvature, and the other one is some sort of effective dilettante type thing. And the scalar curvature one is how you can translate, which Starobinsky did not do, to get an effective potential for Starobinsky inflation, which is in many respects considered to be the leading model for reasons which I don't understand. You get a flat potential. And you also get the interaction with matter in a novel way, which is fantastic. But we used the same trick for what we called Higgs inflation, which is Higgs inflation, in the same paper, which also gave a flat potential. There was somebody at the Institute for Advanced Study, was famous in his day, Adler, who was also pushing these models. So you could see everything was on the table of what these ideas were. And what we did with his variable Planck, we made it more general. But that's too much of that. But I had tremendous fun. And then, even before, well before, the supernova, or the CMB plus LSS, the discovery of lambda, or whatever it is, really the standard model was the dark energy model. So we were thinking about that, and you could get by these mechanisms supercritical acceleration, which is, of course, all being discussed now because that's W less than -1, which is actually okay as long as you don't make it happen forever. It's like a ghost, but the ghost is under control. Anyway, that's too much of that. It's what I'm going to try and do is to show you that the Hoyle-Narlikar ideas, if you follow them through, are actually the ideas that are fundamental in our discussions of the early universe these days, and there was no way that they should have been ostracized for having this model. Okay, so after Planck 2013, these ideas were dusted off by Kalash, misspelled, and Andre Linde, and it's called the alpha attractors. And in the meeting I was at last week, almost everybody, it's all alpha attractors, all alpha attractors. But the whole thing is going back to them, and JBD, but them. So then, you should think of Hoyle and Narlikar as trailblazers and not being out there with a steady state. Now, the other thing that happened is that they went beyond that conventional concept of steady state, and they rethought, in the sense of rethinking cosmology, or reimagining cosmology, as I like to say, as a quasi-steady state. And Burbage joined that paper, but it was basically Hoyle and Narlikar. So I met up with Fred in Cambridge, and I also talked extensively with Jayant about this, trying to get them to not get so excited about the concept that the little bang would be the pouring out of AGNs. That is to say, it was, direct within our horizon. Just make it a little bit bigger than our horizon, and that's the standard model of cosmology. And so this was the point I was trying to make, that it's really front and center. So I said, just make the little bangs a bit bigger than the size of the horizon, then your steady state is called semi-eternal stochastic inflation. And most of the volume of the universe is inflating under that picture. And every now and again, you go through a reheating period, and that's the little Big Bang, or the Big Little Bang, or whatever I called it there. And so it's actually the model of the universe. So the picture I have is that Fred Hoyle and Jayant now, because he's also passed away, are sitting at the end of the universe, and they're looking back, and you're all going to come up and knock on those pearly gates and say, what is the answer? And the Cheshire grin will come from Fred Hoyle and Jayant Narlikar saying, see, told you. But it doesn't mean that Gamow was wrong. It just means that it's the unified picture. So then a lot of press has happened, and you know this, and he actually got a Nobel Prize, not for this work, but Penrose. He has been working on the conformal model of cosmology starting around 2005, 20 years, did detailed searches for what came before the Big Bang, through the Big Bang, so that you could see it in the CMB data. He's not the only one that's tried that, but it's a little bit similar to try and find the iron core that passed through the time zero. And so, we in the trade didn't think that they were doing the right thing statistically, but it didn't mean that you shouldn't look for it. You should look for it, because the outrageous may be how Mother Nature decides that things go. And really, the steady state theory was not outrageous. It is actually the standard model. So now in string theory, you ask yourself, what's the status of all of this stuff? Well, the dilaton is fundamental in string theory, and there's an axion tied to the dilaton. I think that maybe the combination is the way to save Hoyle-Narlikar, for reasons I'll get into a second. And then more generally than dilatons, there are all these other collective degrees of freedom. They're called moduli, each of them with their axions. In other words, the language of string theory is in effect an outgrowth of the language of Hoyle and Narlikar. So I cautioned in my lecture on Monday, question authority. And here I am saying authority, like Witten, makes you think that maybe Hoyle and Narlikar were onto something really quite profound, which they were. Okay, but the worry is, number one, now Elon Musk Grok knows my thinking. We had an in-depth discussion about this whole situation. And then it came back a little later and had completely incorporated what I said with no attribution, but that's okay. And so said, yeah, this is the problem with Hoyle and Narlikar. And the problem is the one that I actually talked about, emergence, which is what actually happens at the zero. Because the conformal field that they were thinking of is one that was really quite coherent, because it's going to mimic a Big Bang that's going to do this kind of oscillating work. And what you expect is it's actually fluctuating a lot. And the zero would be fluctuating even more. And so where did the coherence come from? That's question number one. And then the zero crossing should be fuzzy. That's associated with differential acceleration. This is more than you needed to know. But the same issue arises in de Sitter space. There is no such thing as de Sitter space, as I'm sure you're aware, because de Sitter space is always fluctuating, and fluctuating in a big way. And so it's intimately related. In other words, Hoyle-Narlikar is front and center in the class of ideas. And you will be happy to know it's back to pictures. The picture is the tree picture with something which I thought this was going to be the last thing, but I guess you're going to do something. So it's cheers to the giant of India. I put the Shri in front because I think that's the mark of great respect. May the trees you planted and nurtured continue to bear fruit. And then, of course, you can all read the Hindi. I can't, but I grabbed it. It means bear fruit. And then I look, happy to see, but I've been here a lot. I see the current and future gardeners here and now. And what we're going to do this evening is we're going to celebrate Jayant with a party, a banquet, a feast of ideas. And let us continue that. And so that's the point that I think that I will end on, although we should remember him as we raise our glasses, whatever is in them, this evening as we have our banquet outside, because he was a remarkable, relatively quiet, but very profound in terms of impact individual, and we should all applaud him and celebrate him as a great Indian scientist who actually did great scientific work as well as great building work for the edifice of science in India. No questions.
So thank you, Dick. I mean, oh, is there a question?
Are questions allowed or no?
Sure, why not? Well, I don't know. You're going to speak? Oh.
No, Subir.
Oh. Well, anyway, yeah, you're going to speak. Okay, good. Sure.
Okay, so with just one comment, I mean, those of you who are history aficionados, Don Clayton has a whole web page with series of photos of nuclear astrophysics going back to 1959 with Niels Bohr and all that. So I just have one question. I mean, you said the Hoyle-Narlikar gravity is similar to Brand's-Sticky theory. So how does it, what are the solar system tests, how is it different? And just one sociological thing, I mean, if you look at the classic textbook like Steve Weinberg's 1972 book on cosmology or Cliff Will's 93 book on theory and experiment in gravitation physics, so they discuss Brand's-Sticky theory extensively, but they don't discuss Hoyle-Narlikar gravity, although Steve Weinberg's 72 book does discuss steady-state cosmology. So do you know the reason, or anybody else?
Well, first of all, there was not universal embracing, as you've heard, with Hoyle-Narlikar. And, going through the zero is a non-trivial thing that nobody really knew how to do. Mr. Grok, or is it Mrs. Grok, or Madame Grok. Anyway, she said that Hawking had a complaint, which was somewhat related to mine, but it looked to me like they just grabbed my words and then said, Hawking said it. So, you know, it was recognized that there were issues. The JBD theory is far, far beyond the explicit thing that Brons and Dickey put in place. I mean, they had a really interesting concept, which was really good to look at. And again, it did not get universal engagement in the community, which was that the sun would have a quadrupole, and you could get that quadrupole by measurement. And Dickey was one of the great measurers of all time. And so he was actively looking for this in the sun, and the consequences would have been enormous, but it hasn't, of course, been seen, and now we know so much about the sun, it's not the case. But the thing is, you had all these degrees of freedom in describing JBD theory in terms of potentials and other things. So it was all things to all people, and it was just that they were working on a simplistic version of that that would have constraints, because what was happening in the solar system would be intimately related to what was happening in the exterior universe, a very large out. But you know, this is one of the things that we do. It's actually a JBD type theory that's called quintessence. And the way it works is that there is a natural term that can arise called screening, in which you're basically turning it off when you're within the solar system. And so you don't have an effect, but the effect occurs far out. And this may come as a surprise, but that could be the answer to everything we've heard associated with the dynamical dark energy that's coming out of the DESI plus other stuff. And it would actually sort of work, and it's a fun theory to think about. But yes, so there are very many versions of the JBD theory, and you could do the same thing with the Hoyle-Narlikar. And in fact, you could say that Steinhardt and Turek did exactly that. They have their own version, but they certainly wouldn't have invoked the names Hoyle and Narlikar, unfortunately.
I need the microphone.
Oh, yeah.
Okay. Now I invite Professor Subir Sarkar, a renowned cosmologist and particle astrophysicist from Oxford University. Subir, like many other leading Indian scientists of Indian origin worldwide, was trained in India and had a great career all over the globe. But unlike many, Subir has remained extremely closely associated with the Indian science community, serving as an advisor to institutions and science endeavors in India, and also as a guide to many researchers. So over to you, Subir.
Thank you, Tarun. I should say, thank you, that I've never worked with Jayant either as his graduate student or colleague or collaborator, but I've really known him for the longest of anyone in this room, because I was a graduate student at the Tata Institute actually 51 years ago, and Jayant had just joined the institute, I think, 4 years earlier, 3 years earlier. I was not a student because those days you were only, you could only work with the person who had in fact picked you out in the selection interview, and they only chose about 5 or 6 people. And in fact, I joined the Cosmic Rays group and worked with Sukumar Biswas and Ramnath Kaushik, who was mentioned as having been on the IUCA advisory committee at some stage. Yashpal was his supervisor, so there is a lineage there. But the contemporary of mine who in fact became Jayant's student was Dhurandhar, who many of you know here, who in fact was very instrumental in starting the whole gravitational wave study in India. But I had no direct interaction with Jayant, apart from the fact that he lectured to us in the TIFR graduate school, as it then was, on general relativity and cosmology. And as you might imagine, Actually, you can't imagine that, because most people, when they think of Narlikar, they think of somebody who had, crazy ideas. He was absolutely meticulous and pedagogical when it came to lecturing. And none of all these ideas that you heard about came into his teaching, which were to the point and covered the material that we needed to know in scrupulous detail. Now, he was actually quite approachable. In particular, I recall on weekends he used to put on a red kurta and pajamas which were slightly too short. And we graduate students used to be quite amused by this. And, and he was always possible to approach him and talk to him. But most of us didn't do that because he was clearly a serious person, and you only went up to talk to him if you had something to say, not just to shoot the time of day. So I can't say that I knew him very well, and then of course he went up to IUCAA and did all the things that you have just heard about. But I should say that he made a deep impression on me nevertheless in my very first year at TIFR, or maybe the first summer rather, because this was the time, shortly earlier, before that, Govind Swarup had built this radio telescope at Ooty. He had driven around South India to find a hill with the same slope as the local latitude, so that it would scan in right ascension automatically without any moving parts. And he had got TCS, the Tata Consultancy Company, to actually build the damn thing. And Vijay Kapahi was Swarup's graduate student who had undertaken his thesis on measuring the angular sizes of radio sources which were being occulted by the moon. That's a very good way to measure the size precisely. And Kapahi gave a colloquium, Wednesday colloquium in TIFR. The room was packed. And he concluded that the data provide evidence of evolution with such properties that it's hard to explain the data with the steady-state theory. And Jayant was, of course, sitting there in the second row, I recall, and he rose to speak after Kapahi finished, after an hour. And this was an example that made a deep impression on us graduate students, because we saw in action how a scientific debate is conducted. So he was soft-spoken. He never shouted, as those of you who know him can vouchsafe. But he argued that the data was simply not good enough to come to that conclusion and could not distinguish between the evolutionary and the non-evolutionary models. I'll show you the data in a minute so you can judge for yourself. Now, to be honest, we were in our first year. I don't think we followed the argument in any detail. But what we did pick up was that this was how you did science. You do not pick a personal fight with the person who is attacking your theory. You look at the data, you look at the statistics, you make a coherent and cogent argument as to whether you might agree or disagree. But you have etiquette and respect for the person you're speaking to above all. And that, I think, is something that the little that I've learned out of I got from that encounter, and I still remember it now 51 years later. Now, I was amused to read some years later, actually quite recently, Jayant started writing a blog in recent years. Some of you might know it. And he talks about this incident which happened at the Royal Astronomical Society in London in '61, when there was a debate in which Jayant intervened between Hoyle and Ryle, who was mentioned earlier. And Jayant's intervention on that occasion was something he didn't really want to do. That's what he says in his, the blog address is here in case you want to look it up. And he describes how he was more or less pressed into doing this, which he did reluctantly, but it actually made a big difference. It was his first public on a very public platform, meeting somebody who was a real, central figure of British science, etc. And I wish I could have talked to Jayant at some point about how it had felt for him to be confronting the establishment in this manner on their own ground. But that's what he says in his blog. So this is, I looked up Kapahi's paper because I couldn't, of course, remember exactly what he has shown. And indeed, he's showing the data for the number of radio sources bigger than some angular separation here as a function of the theta. This is the data from the Ooty telescope. And he combined with data that he had got from the third Cambridge catalog, etc., which you see here. And basically, this dashed line that you see here, that is the steady state theory. And this is a particular evolution track in the standard cosmology. And I think, I mean, you don't need to do fancy statistics on this to tell that you can't actually tell the difference between these two lines with that data, right? And that was Jayant's point. And I think I would agree with him to that extent. However, as we all know, the discovery of the microwave background changed all that. Dennis Sharma, who I worked with, went to work with in Oxford, in fact, recanted immediately. But actually, to be fair, it was not until 1992, when Kobe measured this black body spectrum, that the steady state theory was definitively rejected. Because in order to make a black body as good as that, Hoyle had already proposed how starlight could be converted into microwave radiation with the right spectrum, with a specifically shaped graphite needles or whatever. But the fact you need an optical depth in those needles which would be so high that it would blot out your view of the external universe if you tried to make a black body as good as that. So I think this was the end. And at this point, I have to say, one wondered why Jayant didn't let go of the steady state. And even in 2000, they wrote this book. And one did wonder why they were still sticking to what became a kind of a diluted version, the quasi-steady state. I didn't quite get that. But what was amusing is this famous picture from that book, I think presumably taken in Yorkshire, where Fred comes from. And it shows this flock of geese, and it says, this is our view of the conformist approach to the standard cosmology. We have resisted the temptation to name some of the leading geese. So, I got to meet Fred because after he retired from Cambridge, he lived on the south coast and used to come up to Oxford now and then. And I did ask him about this picture, and he said, you have missed something. These geese here, they're actually going in the backward direction, if you look at it carefully, okay? Now, we have to admit that although, I think to be honest, most of us would have considered it time to give up the steady state theory at this point. But it is quite true that although the standard hot Big Bang has proved to be immensely successful, at the culmination of the model today in this lambda CDM, which you keep mentioning even when it is not actually relevant. So all the discussions about dark matter today were actually about the CDM. Lambda was not at all relevant, but we still call it that. In any case, neither of them have been detected yet, and for many people, that is still a flaw. But I should say at this point that even though I couldn't understand, Jayant's, we used to call him JVN, and I'll continue calling him JVN because we didn't call our teachers by their first names those days. So JVN basically became concerned more recently about the fitting of supernovae to extract this evidence for acceleration. And I have highlighted a couple of papers that he wrote in this context, where he says things like, instead of using the data to test the model, studies seem to concentrate on assuming the model to be correct and limiting themselves to estimating model parameters. I'll show you in a second what they mean. And therefore, the important purpose of testing a theory is vitiated, and similarly here. And actually, this kind of inspired me to look at the supernova data, and we found that, in fact, what he's saying is quite true. The supernova cosmologists were doing something called the constrained chi-square method, where they would construct a chi-square in the usual way, the observed magnitude minus the theoretical one in the model, squared divided by sigma square. But then they added a term to each data point, an arbitrary error, which was then adjusted until they got a chi-square of 1 per degree of freedom. Okay? Now, this is valid if you just want to estimate the model parameters, but that does mean that this method is useless for then selecting between models, right? To do that, you have to do a maximum likelihood estimator, and that had not been done by the supernova people until this time. This is 2016. When this is Jeppe Nielsen, my graduate student at Copenhagen, where I then was, and Alberto Bufanti, we looked at the data and we constructed a maximum likelihood estimator instead of doing this fudge of adjusting the chi-square to fit it to the assumed model. And in fact, we found that if we just construct a likelihood based on the simple and quite reasonable assumption that the supernovae don't know about cosmology and vice versa. So the probability distribution of the supernova fit parameters are independent of the cosmology parameters. And in fact, the light curve fitting parameters are consistent with being Gaussian. So one can just integrate these things if they're Gaussian distributions in 2 lines and get a likelihood in 2 lines. And that actually then shows that the data cannot really distinguish between a model in which the universe is expanding at constant velocity, the so-called Milne model, and the decelerating model, and the accelerating model. And this, to me, was actually quite a wake-up call, because one had been told that there was definitive evidence for acceleration, and this didn't look like it. And more recently, we have been looking at the anisotropy of the acceleration, if there is any, because if it is due to lambda, there can't be anisotropy. And Animesh Shah, who is here, with whom we have been looking at the latest supernova catalog, Pantheon Plus, having done it earlier with JLA, and we find that there is a significant dipole in the acceleration that is inferred, extending out to a few hundred megaparsecs. And you might hear about this in Christos Sagas' talk tomorrow. And the dipole is not quite in the same direction, but consistent in the broad direction with the CMB dipole. And I've already told you earlier this week about the fact that we also find another dipole anomaly, in that even if we boost to the frame in which the microwave background is isotropic, in that frame, the distribution of quasars and radio sources is not isotropic. There is a mismatch between the expected dipole from our local boost and what we actually observe on the sky. So let me conclude by saying that Narlikar, or JVN rather, was keen on having a paradigm shift in cosmology. And this might be happening now, although from a different direction perhaps, because his steady-state theory was actually motivated by what was called the perfect cosmological principle, which was Bondi's extension, Bondi and Gould's extension of the usual spatial cosmological principle to make the universe independent of where it was in time. Now that was ruled out by the discovery that we did have a hot dense past, as evidenced by the microwave background, but the spatial cosmological principle has lived on. And as Weinberg wrote in his textbook, the real reason is not that it is correct, but rather that it allows us to make use of the limited data afforded to cosmology by observational astronomy. And Weinberg did highlight the fact that if the data will not fit into this framework, we'll be able to conclude that either the cosmological principle or the principle of equivalence is wrong. Nothing could be more interesting. And yet we seem to have forgotten about this in the intervening time. And the data has now arrived, so now I think it's a very exciting time to start doing cosmology. But let me conclude by saying that I feel, with regard to JVN, something like the character Eklavya, which all Indians here know about, somebody who didn't actually learn, Eklavya didn't learn archery directly from Dronacharya. He observed him at a distance and appropriated his way of looking at things and his style. So in that spirit, let me give my respectful message to JVN in the Sanskrit, so forgive my rusty Sanskrit, but what I would like to then say, Akhanda Madalakara Vishala Yana Characharam Tapadra Dashikta Yana Tasme Shri Guruva Namaha. And if you don't know what that means, there is the translation here, and from that you can see that I have never actually thought of JVN as someone whose science I necessarily entirely believed in, especially his adherence to the steady-state theory, after it clearly seemed ruled out by observational evidence, but indirectly by giving one the feeling that one ought to be able to challenge established notions, mainstream notions, facts that are apparently upheld by distinguished people without any concern as to whether they are ultimately true or not. JVN taught us to challenge these things, to have the courage to look beyond the obvious. And for that, I'm truly grateful, and I appreciate the fact that Tarun has allowed me to say that here. Thank you. You say something?
No, I'm not good. I would, I'm really, happy beyond words because I never expected such a rich tribute in terms of cosmology and also so well thought. So, actually I put together, I've tried to understand Jayant because he actually is formally my supervisor, although he handed me over to Varun, in his formal way, and he never interfered after that, never asked me what I was doing. So that was amazing about him. So he was a person, I saw him at I don't know about the whole science and also, what I had in my slides were my readings of what it is. And I think, people have masterfully talked about it, and I don't want to spoil the fun. But certain things that struck me were this sense of being principled. And, when I sort of navigate in the academia in India, I always find that at total odds with what I saw Jayant doing, right? So for example, I was working with Jayant, and I must say I was considered a good student. I mean, I came from a very good school and then joined physics. And I was working with him, but when I told him that I would like to explore working with Varun, he allowed me, very readily to do so. He would have also, he wanted me to consider Paddy, but Paddy had not moved. But what was remarkable is I never, during the time that I worked with him, did he ever say, work on this theory. In fact, I remember Jeff Berkbridge coming in and saying, why aren't you getting all these guys onto the steady state, whatever, saving the steady state. I somehow, although he never sort of admitted to this, but my career starts almost at the same time that COBE announced its results. And I can't imagine someone like Jayant not realizing the import it had for steady state, okay? And just like Subir said, I mean, what struck me is, although people said all kinds of things about his physics, I mean, he taught, quantum electrodynamics. I thought, I had learned it in undergraduate, but I'd never had such a clear set of lectures. And, so there was nothing, that he was definitely a very, very, very well-trained physicist and this thing. And the other thing is, how steadfast he was to any principle that he had, right? The way he ran IUCA, his principle was the day of faculty joins is part of the decision making. Okay, then simple things like, we couldn't interfere in each other's graduate students. He said, supervisor has the last word on a graduate student. And all the problems that I see around in other places, I see he had, in these strokes of very principled way, he had solved them in IUCA, and that remained that way for years. I mean, and I think in that sense, not only was he a, great scientist, and people have much more to say about him, but I found him an amazing person, and so devoted to whatever he thought was the right cause. Okay, so I'll not stand between you and the banquet, and so I hope all of you would join us the lawn, and thank you again, Dick, for this remarkable tribute, and Subir for the tribute, and of course, mine I put myself in because Varun, couldn't come, but I'm sure he would have given another perspective which would have been interesting. But thank you so much for joining us. Hospital